Good morning everyone. My name is Pranav and I am from Institute of Aeronautical Engineering IARE, and today I am going to talk about the subject engineering physics, and the topic today I am going to talk about is crystal structure algorithm, a methodistic optimization method, which is an interesting and little bit tough topic in engineering physics. Crystal structure. What is meant by crystal structure? First, let us know about crystals. Crystals are actually the solid with atoms, ions, or molecules arranged in a precise and repeating pattern extending in all three spatial dimensions. They exhibit long range order and symmetry, which determine their mechanical, thermal, optical, and electrical properties. Engineering physics focuses on understanding how atomic scale arrangements affect macroscopic behavior. The study of crystal structures forms the foundation for materials engineering, nanotechnology, and solid state physics. So basically, three spatial dimensions is like the dimensions around you, around your surrounding, whether it is in a chair, in your bed, or on your table, wherever it is. And in the 3D space, so many crystals in form of atoms are present and are actually equally arranged in a well manner, like in a stadium, the arrangement of seats in equal way. Now coming to crystal structure algorithm. A crystal structure algorithm is a computational method used to determine or simulate how atoms organize themselves into periodic patterns. It integrates mathematical models and physical laws to calculate lattice parameters, atomic coordinates, and bonding interactions. Modern algorithms can reconstruct 3D atomic lattices from X-ray diffraction or electron microscopy data. They are essential for predicting new materials and understanding structural defects in existing ones. So basically, crystal structural algorithm is like a method used to determine how atoms organize themselves, how in which patterns, in which periodic patterns, in a well mannered way, or what. It integrates mathematical models and also the physical laws to calculate lattice parameters, atomic coordinates, and bonding interactions. Modern algorithms can also be reconstructed by using 3D atomic lattice from X-ray diffraction or electron microscopy method, which are essential for predicting new materials and understanding structural defects in existing ones. Now, the concept of metamorphic synchronization. What it is about, and is it a method or any other new thing? Metamorphic synchronization is a dynamic technique that ensures the consistent alignment of computational models during phase or structural transformations. As crystals undergo changes due to temperature, pressure, or chemical conditions, atomic positions must be continuously recalibrated. This synchronization helps to maintain energy balance, lattice stability, and continuity between different structural phases. It functions as a self correcting loop within the simulation framework, ensuring realistic modeling of metamorphic behavior. So, basically, metamorphic synchronization is like a method uh, that ensures consistent alignment of computational models during phase or structural transformations. When a crystal undergoes changes during high temperature, high pressure, or low temperature, low pressure, it must be recalibrated. So the synchronization method actually helps to maintain the energy balance, lattice stability, and continuity between different structural phases. Why synchronization actually matters? In real world conditions, atomic configurations evolve dynamically, especially during stress, heating, or cooling process. Without synchronization, Numerical simulations can become unstable, producing unrealistic distortions in the lattice. Metamorphic synchronization prevents data divergence by regulating time step transitions and ensuring consistent boundary conditions. It also allows research to simulate complex behaviors like grain boundary migration and polymorphic transitions more accurately. So, in real world, the atomic configuration evolved very dynamically. Previously, I said like during stress, heating, or cooling process. Without synchronization, it's hard to maintain them. It becomes really unstable. Metamorphic synchronization prevents data divergence by regulating time step transitions and ensuring consistent boundary conditions, which also helps the researchers to stimulate complex behaviors like grain boundary migration and polymorphic transitions more accurately. Working principle: initializing atomic positions and define boundary conditions for the crystal lattice. Apply external parameters such as pressure, temperature, electromagnetic fields. The system detects deviations in lattice symmetry or bond energy distribution. A synchronization feedback loop adjusts Atom's coordinates and simulation parameters to restore its balance. The algorithm updates until a new stable configuration is achieved, representing a metamorphically synchronized structure. So basically, it is the working principle. It initialize atom position, apply external parameters such as pressure, temperature. Mm, it the system detects deviations in lattice symmetry. The synchronization feedback loop adjusts atom coordinates. The algorithm iteratively updates until a new stable configuration is achieved. Now coming to the applications, it is used in simulation of deformation in metals and alloys under stress or temperature gradients, helps in analyzing phase transition in ceramics, superconductors and nanocrystalline materials, helps in analyzing phase transitions in ceramics, superconductors, and nanocrystalline materials, supports the design of metamaterials with adaptive optical or mechanical properties, improves precision in semiconductor crystal growth processes such as silicon wafer production. So, these are the basic applications you must know. Used in simulation, help in analyzing phase transitions, supports the design of metamaterials, improves precision in semiconductor. Now, coming to the advantages, it enhances the accuracy and stability of structural predictions across varying thermodynamic conditions. It reduces computational errors by continuously adapting to lattice reconfigurations. It can model hybrid materials and complex composite systems with better precisions, supports integrations with molecular dynamics and density functional theory DFT for deeper insight. So the advantage is like it can model hybrid materials and complex composite systems. It can enhance its accuracy and stability of structural predictions, supports integration with molecular dynamics and density functional theory, which is also known as DFT. Now, coming to the limitation and challenges. The algorithm complexity increases rapidly with the number of atoms and elements involved. High performance computing resources are required for large scale simulations, calibration, and validation using experimental data. Example XRD or TEM results are crucial for accuracy. Managing synchronization errors in quantum level simulations remains a major research challenge. So the one of the toughest challenges like the algorithm complexity increases rapidly with the number of atoms and elements involved. So even synchronization is like it can't help high performance computing resources because it is required for large scale simulations. and also calibration and validation using experimental data are crucial for accuracy. And also managing synchronization is difficult because it shows errors in quantum level simulations remains a major research challenge. Coming to the conclusion, metamorphic synchronization ensures stable and realistic modeling of dynamic crystal transformation. So crystal is like arrangement of atoms or molecules in a well proper manner, and metamorphic synchronization provides bridge between status lattice algorithms and real world material behavior with advancements in computation and AI. This technique will play a key role in next generation for materials engineering, applied physics research, and also in nanotechnology. Thank you.